Okay. Assalamualaikum warahmatullahi wabarakatuh and hi everyone. My name is Nur Mimi Ida Yubenti Ismail from group AS2291B. So my topic here is heavy metal in river pollution. Okay, the first one is introduction. Information on the levels of heavy metals in the Malaysia aquatic environment is scarce and limited to a few studies. Most of the coastal resources, agriculture and economic activity and human population are concentrated on the west coast of Peninsular Malaysia. However, the Strait of Malacca on the west coast is a major international shipping lane and the related maritime activities may also contribute to the pollution of the marine environments of Malaysia. Oil and gas related industry are developing rapidly along the east coast of Malaysia, with most of the development located in the states of Pahang and Terengganu. Okay. The objective of this paper was to review the status of the Malaysian aquatic environment with respect to heavy metals. Much of the work on metals focus on measurements in biota and sediments, but very little research has been done on dissolved and particulate matters, biodegradability of metals like cadmium, copper, lead, plumbum, and zinc. Receives mass attention, but due to technical difficulties, arsenic, mercury, tin, and other hydrate elements have not been well studied. Okay, next is sources of metals. As you can see here, there are four sources of metal where the manufacturing sector is regarded as the major contributor of metal pollution in the environment. Of these metal finishing processes such as electroplating, etching, and preparation of metal components for various industries. These processes has been identified as a major sources of waste containing high concentration of cadmium, copper, zinc, nickel, iron, aluminium, manganese, chromium, and stannum. The second one is electronic and semiconductor industries in several states of Peninsular Malaysia contribute more than 69,000 meter cubic per annum of sludge containing heavy metal in 1992 and in 1992. And the third one is the agriculture sector also contributes some waste containing metals. For example, copper from piggery waste has been correlated to contamination of sediments and molecules in the Malacca Straits. Port and shipping activities contribute to pollution by tributyltin (TBT) as well as plumbum, copper, and arsenic. The last one is mining of tin, iron, copper, and gold may further contribute to contamination of water by some metal, although not much work has been done in this respect. Most of the manufacturing industry are located in the west coast of Peninsular Malaysia, and thus more of the studies on metal contaminations have been focused there. Only a small numbers of study has been provided data for the east coast. Okay, next let we see the result. Okay, the first result is heavy metals in sediments. The concentration of heavy metals in sediments from the coastal and offshore waters of Peninsular Malaysia have been extensively studied. While a small number of studies have been provided some data for East Malaysia, as you can see in table 1, the rivers of Peninsular Malaysia in areas with heavy industry and large human population also been studied. The sediments of rivers receiving extensive pollution from industry, sewage, and runoff in highly populated areas have been found to be polluted with plumbum, zinc, and copper. Lead concentration in the Juru rivers in Penang were up to 117 micrograms, and while copper was up to 144 micrograms and zinc up to 483 micrograms. This meter come primarily from a sewage treatment plant that emptied into the rivers. Screenshot analysis have been useful in identifying sediments that are anthropogenically contaminated. Refer to the Lim and Q at 1995 show that non-resident zinc at one particular sampling point in the rivers accounted for more than 80%, while the proportion of non-resident plumbum, copper, zinc, and ferrons were also relatively high. The main pollution sources was identified as the sewage treatment plant. The Langat rivers in Selangor as you can see here, was heavily polluted with zinc and cadmium, with level of 71 to 374 micrograms and 3.1 to 37.9 micrograms. In comparison with natural average global shale values, plumbum in Juru rivers was about 5 times higher than natural values, which is 20 micrograms to 1, while copper was 2 times higher shale values of 45 micrograms to 1, and zinc was 4 times higher shale value of 95 micrograms to 1. Natural cadmium levels in shale were 0.3 micrograms to 1, and thus the Langat rivers were highly contaminated with cadmium. In marine sediments from the coastal environment of Peninsular Malaysia, concentration of plumbum indicates some enrichment above the natural global values in shale in the coast of Kemaman, Tanjung Karang, and of Juru, Penang. In the Johor Strait between Malaysia and Singapore, plumbum and zinc were higher than global shale values by a factor of 3 and 2 times respectively at sampling sites closest to the causeway linking Malaysia and Singapore, which receive very high vehicle traffic. The plumbum enrichment was probably due to the use of leaded petrol and zinc from tire wear. The concentration of most of the metal studies in coastal and offshore sediments of the Malacca Strait and of the South China Sea of Peninsular Malaysia and East Malaysia were similar to global shale values and can be regarded as baseline values. Normalization of metal concentration to aluminium have frequently been used to differentiate between anthropogenic enrichment and natural metals values, and the use of this method show that zinc was higher than the global shale values. Why? Those copper, chromiums, and nickel in the South China Sea sediment were lower. Elevated levels of metals in coastal sediment may be attributed to anthropogenic input. When values are higher than global shale values in sediment from regions of the South China Sea, far from the mainland, it may be due to the sediment grain size, mineralogy, and organic matter content. Okay, the second one is metal concentration in water. Okay, as you can see here, published data on trace metal concentration in rivers and marine environments of Malaysia are especially scarce due to the difficulty of measuring the metal at the sub-ppb levels. Data from metal requiring hydrate generation in their analysis, such as mercury and arsenic, are scarce. The Department of Environment, Malaysia carry out regular monitoring of the water quality of rivers, but reliability of the data has not been reported. The few reliable studies in metal concentration in rivers, as you can see in Table 2, indicate that these rivers were possibly contaminated with plumbum, copper, and zinc, although the values were still within the safe limit for drinking water. Okay, next is metal concentration in biota. Okay, unlike other environmental media, the use of biomonitors to study heavy metal pollution in the Malaysian environments has received widespread attention. Bivalves, Pernaviridis, and Sarcostria species and also gastropods type species were frequently used, while fish were used mainly in relation to health concerns as a result of fish consumption rather than as indicators of heavy metal contaminations. In these studies, cadmium, copper, plumbum, and zinc has received attention. However, due to difficulty in analysis, arsenic, mercury, tin, and other hydrate elements have received little attention. The result of measurements in fish, bivalves, and shrimp in Table 3 indicate that there was very little cause for concern with respect to contamination by heavy metals. However, in gastropods such as the predatory type species, levels of plumbum and cadmium were elevated as a result of transfers from the rock oysters, which is Sarcostria species, on which they feed. In addition, cadmium was elevated in rock oysters from some East Coast location and may not be necessary for due to the metal pollution since some of the sampling sites were away from known sources of pollution. Thus, natural levels may be above normally accepted as baseline values. Okay, next we see the bioavailability and bioaccumulation studies of metals. Reports on the assessments of bioavailability of metals for bioaccumulation by aquatic organisms are very scarce. Bioavailability of metals may be estimated from reports where data for both water and specific biota is available. Bioconcentration factors of 132 to 12,900 multiplied with 103 and 580 to 76,000 and 481 to 70,200 were estimated for copper, plumbum, and chromium respectively. In Rock Oyster from Columbine, Kemaman referred to the Sazili at 1995 and Lim at 1998 reported that BCF values of 0.9 times 10 per 3 to 1.9 times 10 per 3 for plumbums and 8.0 times 10 per 3 for copper and 2.6 times 10 per 3 to 3.3 times 10 per 3 for cadmium for the oyster Carostria belcheri and similar values for sea Iredella culture for 6 months in the Merbau estuary. Refer to the Yap at 2002 studies methods in specification in sediments from the west coast of Peninsular Malaysia and found significant correlation of cadmium and copper in the green leopard mosses, Perna viridis, and with the easily freely leachable and exchangeable fraction in sediments. However, the data were based on a small number of 10 samples and P. viridis is normally found attached to the substrates in the water columns rather than on the sediments. Studies on the fate and effects of metals in the freshwater and marine environments have unfortunately received no attention and thus need to be given attention in the future in order to relate environmental levels with possible adverse effects on aquatic organisms. Toxicity tests with metal relating bioaccumulation and mortality of test organisms with metal specification is limited to investigating effects of metal concentrations to lethal toxicity and few in relation to environmental parameters such as salinity, water hardness, pH, or temperature. Okay, now let me see the mitigation measures. Industry waste were estimated to be more than 247,000 meter cubic in 1992 for all categories of scheduled waste of which more than 71,000 meter cubic may contain heavy metals. There is adequate legislation in place for the control of pollution of the aquatic environment in the form of environmental quality, sewage and industry effluents. Regulation of 1979 and the Environmental Quality Schedule Waste Act of 1989, there is a need to ensure that smaller manufacturing and waste-generating industry are more compliant with these environmental acts, that there is a better control of pollution from sewage. The gradual replacement of leaded petrol with unleaded petrol will also result in a decrease in environmental plumbum contamination. In conclusion, I can say that the result of the studies reviews here show that there was contamination by plumbum and zinc in the sediments of coastal environments that received waste from areas of high human activity such as the Juru and the Johor Straits. The water of some rivers near major cities and townships such as the Juru and Langat rivers were also contaminated. However, fish has been shown that not be contaminated while some bivalves and seaweeds may have elevated levels of plumbum and zinc. Thus, plumbum and zinc may be of primary concern in future environmental monitoring, as the high-rate generations metal have not been extensively studied. The true extent of contamination by this metal has yet to be ascertained and thus should be given priority in future study. Okay. Lastly, We can minimize river pollution by these simple acts and eventually play a significant role in keeping the rivers clean. Keeping the water clean is everyone's job. So, my recommendation in order to reduce the river pollution is we can fertilize garden and yard plants with manure of compost instead of commercial inorganic fertilizer. Next, we can minimize use of pesticides, especially near bodies of waters. Other than that, we should prevent yard waste from entering storm drains. And lastly, we can reduce it when do not use water freshener in toilet and do not use fresh unwatered medicines down the toilet. Okay, that's all from me. Thank you for listening. Have a nice day, everyone. Assalamualaikum.